The topic is Apache Flink for IoT use cases. And you will also see in a bit that when I say IoT, I use IoT because it's a buzzword here and everyone knows what IoT is, but I have a very broad definition of IoT, as you will see in a minute, but we will get to that. So what I want to talk about today is what I call the streaming architecture. We will see in a bit what that is. Basically a new kind of architecture that stream processing systems enable. And I also want to talk, basically I'm coming from Flink, so I'm talking about Flink and what it does in this space. Then the next bit I want to talk about is IoT. So IoT use cases, what are the properties of IoT use cases, and why I think event-time stream processing is important for these cases. And I will also, of course, explain what event-time stream processing is. And then I will show at the end some use case examples. So before we start, can I get a quick show of hands who has heard about Flink so that I can gauge? OK, so it's maybe half the audience. That's quite good. So before we start, you might be wondering who I am or why I know stuff or why you should believe the stuff that I'm talking about. So I'm working at this company, Data Artisans. We employ the original creators of Apache Flink, and we also employ the majority of the committers of Apache Flink and the PMC members, such as me. And what we do mostly, or 90% of the time, is work on Apache Flink in the open source. And recently, we started also providing the Data Artisans platform, which is more or less a supported Flink distribution, where you get support from us, from people that know Flink. So with this, let's dive right in. The streaming architecture. So for this, we have to take a step back and look at what the architecture during the last few years was, which was the big data architecture, which got started by the MapReduce paper by Google, and then the open source implementation in Hadoop and HDFS. And basically, what you used to do there is you would collect data that came up in HDFS or some other distributed file system. You would then periodically run MapReduce jobs, for example, nightly, to gain insights from this data. But the main thing is that the programs were not running continuously. So always collecting data and then at some point getting insights from this data. And what the problems with this are, one, huge latency. So if you have, for example, some data that arrives during the day that indicates some problem in some system that you're monitoring, you will only notice this once you run your nightly batch job. So then in the morning, maybe the data engineers will see the data and will notice that there's a problem, and then they can react to this. So this can be a huge problem because you lose money if the system fails. And also, a more complicated problem is that putting your data in batches and processing them in batches doesn't necessarily match the natural boundaries in the data. So if there's, for example, a web shop and there's user sessions, then, for example, a shopping session of user might span midnight, which is where you usually start your batch job, and then you can't capture these sessions that are inherent in the data because you manually force your data into batches and process them. So these are some of the challenges that we had in this architecture. And therefore, we need, or some people have recognized this, and most people are talking about this now, for example, in the keynotes, people who are talking about this, is the way for a new architecture, which is a streaming data architecture. And there what we want to have is that we want to react in real time to events as they occur. We want to have applications that are running continuously and can continuously produce results and produce alerts. But while we want to have this real-time processing capabilities, we still want to have the ability to process historical data that we have stored somewhere in HDFS. So a stream processing system should enable new use cases, but should also subsume all the stuff that the old systems provided. And I wouldn't be talking about this if Flink didn't support all of these use cases. So in all of the stuff that I'm going to talk about, you can assume that Flink is very good at doing these kinds of things. So just that we get on the same page, I'm going to quickly explain some contexts. So first is what is actually distributed streaming or distributed stream processing. So let's look at these two terms. So streaming or stream processing is when you have computations on infinite streams of incoming data, which is most data that you have in the real world is infinite. So for example, if you have a web shop, then you infinitely get new events incoming. Or if you have, for example, people in the morning were talking about airplanes and their jets, they continuously produce data that you might want to process. Or if you have the Fitbit or other stuff, they continuously produce data. And then you write your code, and this code can continuously process these elements. So you would have these green boxes would be events that come in. This is your code that processes these, and this produces results, these orange boxes. And then what distributed stream processing is the ability of a stream processing system such as Flink to take your code and distribute the computation across a cluster of machines so that you can deal with very large amounts of incoming data, because one machine would not be enough to process all this data. Then the next important property of stream processing systems is stateful stream processing. So for this, I have to take a step back. So what I showed you earlier is basically stateless stream processing. So you have data that comes in, you process it, and you produce some result. But the result only depends on the input, but not on some state that you accumulated in your application from processing the earlier data. So what a stateful stream processing system provides is that your application can have state internally, so your computation can depend on the history of events that occur. So that sounds very abstract, but in concrete terms, for example, you can have a machine learning model that you continuously update by processing these events, or some other stuff that you learn. For example, if there's a session by a user in a web shop, then the previous actions that this user did in the web shop are also part of the state, because you want to look at them when you process new events. For example, the event that signals that a user is checking out his shopping cart. And this is all good to have, but a stateful stream processing system should also provide features that allow you to deal with stateful applications. Because if you have state inside your application, you also have to provide features to let you update this application. So for example, if you want to update to a new version of your stream processor, Flink, or if you found a bug in your code and you want to update this, then the system has to provide ways to keep that state and move the application to a new version, or to roll back to older versions, or to switch between different versions of the state. And that's what a good stateful stream processing system should provide. And the last feature I want to touch on is event time streaming. So I'm going to go into more detail of what exactly event time stream processing is. But as a quick preview, it is basically the idea that these events that you're processing, they have a timestamp attached to them, and that this timestamp is somehow important. We will see in a bit why it is somewhat complicated to process data with timestamps, because there are some properties in the data or some things that can happen with these events and the timestamps that can make it complex to handle them. But a good stream processor should provide the features to handle streams where the events have timestamps and they're important. And then when we have these three basic properties, or these three basic ideas, this is what the new kind of data processing architecture looks like. So on the left, we have these black boxes. They signify sources of data, sources of events. Then what you would have, I think Kafka was mentioned also before, is a distributed message log or event log that can store these events and that allows other systems to read these events again from this message log. And such a system would be, for example, Flink, which can read from a Kafka log, then do the processing, and then produce some results. And in this example, we have several Flink applications running that each have their state inside, so they're stateful streaming jobs. And they can, for example, produce results to HDFS or to Cassandra. And another interesting thing, if you have a stateful stream processing system, is that you can, instead of going the detour of writing the data to Cassandra and then reading it from Cassandra, you can also directly allow an external system to query the state that lives inside the stateful streaming application. So this is what this is hinting at. So I don't have time to go into this, but if you're interested in this, you can come find me afterwards. So to recap, what is streaming? It is the continuous processing of data that is continuously generated. So in my view, it's pretty much all or most of big data where you have data that is continuously produced and you want to react to it in real time. What's very important is state and time. So state we saw, time we will see in a bit why this is important. And of course, I mentioned it before, Flink is very good at all of these. Otherwise, I wouldn't be standing here talking about that. So let's move on to IoT and event time stream processing. I want to first throw out this little number. So I took this from a somewhat recent article in the Business Insider, I think, and they say that the Internet of Everything, which is, I think, a more general term for Internet of Things, will generate $14.4 trillion of value over the next decade. So just to give you a scale of what some people think is the importance of this, this market, just for motivation. And I mentioned this before, just so that we are reminded about this. So these are some of the potential sources of events in an IoT setting. And so my view of IoT is very broad. So you can have, for example, a Fitbit, all these personal wearable things that produce data. You can have sensors in factories or in warehouses that produce data. You have mobile phones that continuously produce data. You have wind turbines or other electrical grid equipment that produces data. You have, for example, smart home appliances or smart thermostats. Everything nowadays in our world continuously produces data. And therefore, because I come from basically a systems perspective, I have a very simple definition for what IoT is. So I use the term IoT because it's a well-known term nowadays and people like it. But when I speak of IoT, is just what it looks like to the system is a very large number of distributed things. That could be the T in IoT. And they continuously generate a very large amount of data. That is, to me, and to the systems perspective, what IoT use cases look like. And some insights or some important properties of IoT use cases are that data is continuously produced, so we have a stream processing use case. Events mostly have a timestamp attached to them, which is important. So for example, if you have a sensor that says it's 30 degrees now, you probably have a timestamp attached to that tells you at what time you had this temperature. Or in a factory, you want to know at what time something happened, or if the Fitbit reports the heart rate or whatever it does, you want to know the time at what this happened, at what point this happened, and it is important for the analysis of the process to keep this time in mind. Then an important property of this is that these events or this data can arrive with delays. Because imagine there's some user playing a game on his phone, and this produces some metrics, some data, but the phone is not connected to the network, so the data has timestamps, but your system only sees those events once the phone is back on a network connection. Or the Fitbit might only report the data once it's back on a connection, or there might be network slowness, all kinds of things that cause data to arrive with delays. And these events or this data, they also don't arrive in the order of the timestamp, because that would be super easy for a system if you can just assume that timestamps are monotonically increasing, but this is not a reality. And we'll see in a bit why this is a bit of a problem. And also, a not so obvious insight is that most analyses in these use cases, they happen on time windows, because you have this infinite stream of incoming data. What you have to do is somehow slice these events into time windows so that you can reason about them. Because if you just have an infinite stream, you would never be able to finish your analysis. But if you, for example, want to get the average temperature of a sensor, you can say, give me the average temperature every hour, because that is something that makes sense to ask. And then these every hour is, for example, a time window. Or for example, for the web shop use case, a user session, so he starts shopping in the shop until he either cancels or he buys something. This would also be a session in time that is marked by a certain start and an end. And the analysis happens on these, what we call session windows, that the user induces. So now, with this, let's move on to what exactly event time processing is. So, quick show of hands, who knows Star Wars? Some people are still not asleep. So, Star Wars is a popular series of movies, of course. And on the bottom here, we have processing time. So this is the time at which these movies came out. So this is monotonically increasing. And here on the top, we have event time, which is the time at which this episode happens in the Star Wars universe. And so the first episode is episode 4, which came out here. Then we got 5 and 6. And then a bit later in processing time, so the real time when we actually saw these events, these movies, we got episodes 1, 2, 3, and then we got episode 7. So in this example, we see that in event time stream processing, data, in this case movies, can arrive out of order with respect to their actual timestamps, the yellow timestamps. This is actually an example of my colleague Kostas Kloudas, so he came up with this funny bit to visualize a bit what event time is. But now to get, I don't know, more serious a bit is this actual use case. So what we have here is we have our message system, for example, Kafka, this yellow bar. We have our different sources of events, and these gray boxes, they are the actual events that we collect in this message queue. And here on top is a time bar that signifies processing time. So this increases monotonically as we go. And the position in this yellow bar signifies the time at which we saw this event. And the number inside this gray box signifies the actual time at which the event occurred. So what we can see here is that, for example, this little box has timestamp 1, and it also arrived shortly after the actual processing time 1. So there's just a bit of delay there. This 3 also arrived with a bit of delay after it actually occurred, but then we get a curveball, we get this 1, which arrives with a huge delay, because it arrives when the processing time is already 4, but it was produced here. Same for the 2. And then all these other messages, you see here, they're also somewhat out of order. They have more or less delay. So what is the problem with this when it comes to processing this data? So let's assume we want to do windowing on this data, because we want to say, for example, these events, they are temperature readings from a sensor, and we want to get average temperature over these 4-second windows. So if we do the naive thing and do windowing based on the processing time, so the time when we receive these elements, what we get is this. So we have here a window that has the temperatures with timestamp 1 and 3, here we have 1 and 2. There we have some other stuff that is also widely out of order with respect to in which window it actually should be. So the solution to this is to do windowing based on event time, so the actual timestamp of the event. So what we then get is we have this window here, which contains all the events with timestamps that fall into this window. Then we get 5 and 6 here, 7, and 11 and 12 here. So this is the correct way to put these events into windows if we want to produce an average of the temperature that respects the timestamp of these elements. So that's the basic problem of why I think event time processing is so important, because there's a mismatch between the event time, the time at which the event occurred, and the processing time. And there's all kinds of interesting stuff going on in Flink to make this happen, and also in other systems. So Flink didn't invent this. We just have an implementation of this. But if you're interested in this, come talk to me afterwards, because we don't have time to cover this here. So at the end of this section, let's quickly look at what are some of the sources of this mismatch between event time and processing time. So I already mentioned some of the obvious reasons. So the sources of big mismatch, these are network disconnects or slow networks or whatever you have. But the more tricky things are the small mismatch in processing time and event time. So if you might be tempted to assume that a very small mismatch in this time doesn't make a big difference, but it does, as I will show in a second. And the sources of the small mismatch is that just the distributed nature of what we're dealing with. So we have all these sensors that are distributed somewhere. We have smartphones somewhere. There's always going to be a small latency. So this always introduces a small mismatch between the time at which the event occurred and when we see it. So what we at Data Artisans did, we have a blog post that is based on a demo that someone did. It's called Robust Stream Processing with Apache Flink. And in there, we showcase some features of Flink, among them, for example, how it handles state and so on, but also how event time processing is important to get right if you want to get correct results. And the idea here is that we wrote a very simple Flink job that runs just on one machine, so not even a distributed setting. And what we did is we created a source of events that basically generates events from a sine wave, so like this. And then what we want to do is we want to induce windows that have the same length as the sine wave, and then compute the sum of this sine wave data. So if we do this, we expect the sum to be 0, because the sine wave goes up and then goes down. If we sum this up, it should sum up to 0. But what happens if you use processing time windowing, you get this result. So while we should always see 0, so a flat line, we actually get this result because of the very small mismatches between the windows that we should have based on the event time and the processing time where we see it. So if we then switch this program over to event time processing, what we get is this. So on the top we have our sine wave, and on the bottom we have the summed up sine wave in windows with the length of the sine wave. So we get the perfect 0 flat line, what we expect. So to recap, what I mentioned in this section is that IoT use cases, they need proper event time processing. And the subtle but important thing is that even a small mismatch in event time and processing time can lead to wrong results. So it's always important to keep that in mind. Now, with that knowledge, let's move on to some use cases. And I've chosen these two, so King and Bouygues Telecom. I chose those because they published what they're doing with Flink and with event time processing and so on. So in the case of King, in a blog post, and conferences, and Bouygues also at conferences. So if you are interested in this, you can read up on these and read yourself what they're doing. So the first one is King. For those of you, King is basically a maker of mobile games. So they make this Candy Crush Saga, Farm Heroes, some other games. And some people might not expect this, but this is a very huge generator of events. So they have roughly 300 million monthly unique users, and these users, they generate roughly 30 billion events per day. So there's events for everything in these games. So there's, when you start a game, there's an event. When you stop a game, there's an event. When you fail, when you succeed, when you buy, when you do a move, it's all recorded so that the behavior can be analyzed, and you can optimize the game for a user. But the ultimate goal, of course, is to make more money, because you want to learn what the users are doing, and you want to offer them certain offers that they can buy with real money in case they're struggling. And of course, in such a use case, what you need is event time-based stream processing, because all these events that the games generate, they have timestamps, and you want to do your analysis based on when these events actually occur, not when you see them in your system. And what King came up with this is a system called RBEA, which is a system that they developed on top of Flink, that ingests all these events from all these games and then allows the data analysts, the data scientists, that they have to write programs to analyze this data. And what this does is basically it provides a web interface where you can upload little scripts that do analyses written in Groovy, which is, some people might know, it's a scripting language that runs on Java. And what they do is they take so they have one Flink application running, and they dynamically take these Ruby scripts and inject them in the running application so that it then, from then on, processes this data and produces results for data scientists. And they can also dynamically take out these scripts again. So this way they can multiplex a lot of different analysis scripts by the data scientists into one running Flink cluster or Flink application, and therefore have better resource utilization. Because otherwise, spinning up a cluster for every single request would be somewhat wasteful. And then the other use case is Bouygues Telecom. So this is a rather large French telecom. And in 2015, they had roughly 120 users. So this is internal users of their analysis platform that they built on Flink. They had Flink 5 production apps, 750 terabytes of storage, and 4 billion events per day. And then in 2016, they had hugely increased numbers. So now they have 30 Flink production apps, and they now produce 10 billion events per day. And the challenges for them are what you might already expect. They, of course, need low latency stream processing because they need to react in real time to problems occurring. They have, in this case, similar to the King use case, they have massive amounts of data, and the problem with this is that the data is bursty. So during the day when most people are active, you get huge amounts of data, but at night you don't get a lot of data. So the system has to deal with this bursty nature of the data. And of course, it has to be reliable. One tricky thing in their use case is that they do correlations of streams from different input sources to correlate what might be the cause of some failure that they observe somewhere else. And for this, you need to keep state, because you need to keep the history of some stream to correlate it with another stream. And of course, you guessed it already probably, is that they need proper handling of late events because they can have delays and the data can arrive out of order with respect to the timestamp. And this is a slide from their talk at Flink Forward conference in Berlin. And this looks very similar to the figure I showed you earlier about how the new streaming architecture looks like. So on the left, they have their sources. They collect these into Kafka. Then they have their stream applications running using Flink. And then they produce results to Hadoop, to HBase for visualization. And they also produce in real-time warnings if the system detects that there might be some problem. So with this, in case people are wondering, they probably already have a streaming use case because most data in the real world is being continuously produced. In the past, people have used batch processing systems because that was the only thing that was available. But nowadays, stream processing systems have advanced to such a state that they can be used to do real streaming processing, and they can also be used to do the job that used to be done by the batch processing systems. The other important insight is that IoT use cases, and by these I mean pretty much all use cases that continuously generate data, most of them, they require proper time management, so event time handling. And I can't stress this enough, Flink has done that for a while now. So we're now close to releasing Flink 1.2, and we had support for proper event time handling since Flink 0.10. So we had 0.10, then 1.0, 1.1, and now 1.2. So it's quite mature, and several companies are using this successfully in production for over a year now, some companies. So that's it. That's all I have. Thank you. Can I do quick? So if you're interested in this, follow me on Twitter or Data Artisans or Apache Flink. I also want to quickly highlight, we have our own conference planned in San Francisco. So if you're interested in this, search for Flink Forward San Francisco. It's going to be trainings, talks, everything. And of course, everyone is hiring nowadays, so if any of this is interesting, you can look us up and see if anything interests you. That's all I have now, for real.
Okay, so, does anyone have any question?
You can also find me afterwards,
Okay.
in case you want to talk to me privately, but if anyone...
so thank you very much.